All right, I'm here with Bernard Maris, who has a PhD from MIT in mathematics. Thanks for joining us. I'm curious to hear that how you got from mathematics, right, to then find Bayesian modeling to be like a useful tool in your repertoire.
Yeah, so after I left academia and got a job in data science, I was looking at how most people were approaching these data science problems. And it felt like a very piecemeal approach to me.
Hmm.
So I kept seeing things like, okay, maybe you're doing some sort of customer classification problem. And for many of the customers, you have hundreds of data points to use, but maybe for half of the customers, you only have one or even zero data points. Um, and so then doing any sort of regression with those customers where you don't have any data doesn't really make any sense. So then you start building a model and then you add in a special case. Okay, you don't have enough data for these, and so you handle these differently than those. And then also things like, okay, you want to detrend the data and you also want to deregionalize the data. And so which one are you going to do first? Are you going to detrend and then deregionalize? But then that's going to introduce false correlations because maybe the regional has some trends. So you have some customers that emerge in certain regions, and so they get misclassified because they came late in the trend.
Mm.
So I and once you get to that point, you start making these choices of thresholds, choices of which effect do you account for first, that really leads to being tied up in knots. And so you have this model that does something fundamentally very simple, but it's really hard to go in and adjust and to try and figure out, okay, if I tweak this parameter, but it's early in the pipeline, then it may have the opposite effect that you were trying to achieve. And uh, the whole process and kind of non-Bayesian way of thinking really leads to getting stuck, is what I've found. And so I think the Bayesian framework, where you kind of consider all possibilities at once, so there's no single solution. You're considering all the possibilities at once, of course, weighted by plausibility, and that really frees you up from a lot of these knots that you can tie yourself up in. So you can keep the model definition really simple. And of course, there's no free lunch because there's still fundamental complexity that you have to overcome. So there are challenges in getting the model to converge that you might not notice in just sort of a classical machine learning framework. Um, but there's still essential complexity there, but you're dealing with it in a more direct way. And yeah, it's just a lot more easy and a lot more honest
Mm.
in my view.
And a lot more obvious, I guess, and transparent, right? Because the other thing in that piecemeal workflow is, well, there's some things happening over here in some Jupyter Notebook cells, some things happening over here, and then other stuff over here, and someone trying to really read through and like know, well, what is, because that is the model, right? It might not be like one coherent statistical model, but still like all these choices are being made and detrending is happening. But yeah, it's not all in one place. So the holistic aspect that you mentioned, I think, is really powerful. And I often actually, that's how I sometimes like to introduce Bayesian modeling, is to say, well, you already have a model, you just didn't know it yet, right? Like all these steps you're doing in your data analysis pipeline, that is a model. Here we're just like sort of creating one single version of it, and you can run that and have all these benefits you mentioned. It's much more easy to read from someone else what assumptions went into it. So yeah, I really like
Yeah,
that.
yeah, exactly. And interpretability
Mm.
is super important to me. I like to be able to like just tell clients what does some particular thing mean, and not only can you give them a value, you can give them the uncertainty, and you can have more confidence that this is actually the effect that you're talking about, not some piecemeal thing where you're correlated with other effects in some weird way. So
Yeah.
it feels really a lot more correct, and that really appeals to kind of my mathematical sensibilities.
Yeah.
I want everything to be correct.
Yes. So then that's the, I guess, methodological motivation. So you're, of course, with us at PyMC Labs and using PyMC and developing PyMC. What has drawn you to that particular project among the other ones?
So one big thing is that it's in Python, and the majority of data science people out there are using Python. And so it's really kind of the natural choice
Hmm.
from that perspective. And not only that, but you have really wonderful documentation and a very vibrant community. So if you are struggling with some model, there are likely other people who have struggled with equivalent models in the past. And if you have something new, there are lots of people eager to help out.
Hmm.
And the documentation is also very nice. A huge example gallery, so plenty of ideas to pick and choose from.
Hmm. Yeah. Um, a couple of things you mentioned, but definitely I feel the community is one of the strengths. It's just like there's so many people on all sides, right? In terms of like the people who are helping out in the community work, but also the user base and all the interactions on the discourse. And it's really active and lively and friendly.
Yeah, and so what really sucked me in is I really wanted to use PyMC in my projects.
Hmm.
And back at that time, it was very difficult to install. And I was sitting there thinking, I know PyMC is the right way to go, but how do I bring my colleagues and my boss in
Hmm.
on that? And uh, the installation was definitely a big burden. And so I figured, okay, I'll go in and learn a bunch of conda forge stuff and simplify the installation. And then maybe that will help convince people.
Yeah,
Uh,
actually, yes. I totally forgot to mention in the introduction that you're the master of our Conda Forge repository. So if you Conda installed or Mamba installed PyMC and it just worked, you have Ben to thank for. So thanks. I definitely had that many times. Yeah, and like that is also much improved since then. So if you think about where the project is today, and then maybe projecting ahead, what are you especially excited about or think that maybe we should invest more time in and improving in the project?
um, so for me, I get really excited about learning, and I'm just really excited to see what sorts of new models people are building, what sorts of ideas people come up with, and see what works. And just being able to take those ideas and transfer them into new contexts. So I guess that's more of a personal motivation. And then on the more general motivation, there's that thing that I mentioned earlier about sort of essential complexity, and kind of, so you have all these challenges when you implement a Bayesian model, and how much of that is that, um, oh, there's some series of steps that can be automated that you can do to fix up the model, or maybe um, maybe a new sampling algorithm would fix things. So I think it's also really interesting, but also extremely challenging and hard to predict. Like, what can we do on the algorithmic side to make the experience better, um, and make modeling easier, and to kind of automate some of the specialized knowledge that we've developed at labs, and open source that and just make things work better. Yeah, I'd really like to make things work better in general and give everyone a better experience with PyMC and Bayesian modeling in general. Um, yeah.
That's a great motivation. So you did your PhD in topology and differential geometry. Is there any connections you found to Bayesian modeling where you thought like, oh yeah, this was interesting, or has that background been helpful at all, or maybe a hindrance?
Yeah, so funny thing about that, you can go through an entire PhD at MIT without ever having taken any stats or knowing any statistics terminology. So when I transitioned into data science and started learning Bayesian statistics, I was really playing a lot of catch up with the terminology. But there are just so many analogies between statistics and physics that it was really fun to make all these various connections. So, for example, I'm reading about Gaussian processes, and then I realize, oh, a Gaussian process is the same thing as a free quantum field. So
Cool.
it's the
Didn't know that.
same underlying mathematical concepts
Yeah,
bundled up in different language. Um,
fascinating.
and also, there's a really cool physical analogy between classical mechanics and quantum mechanics being uh, being the same as the distinction between frequentist statistics and Bayesian statistics.
Crazy.
Yeah, so roughly speaking, in a classical system, a particle follows a single definitive trajectory. You write down the equation, solve it, and that is the path that something takes. But in quantum mechanics, a particle follows all possible trajectories,
Hmm.
and you have to weight those each with a different phase. And just like in Bayesian statistics, how you have to consider all possible values of the parameters
Yeah.
and weight them with the appropriate probability. So uh, it's 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 a lot more complex, but it's also a lot more rich. Like as you can see how much richer quantum computing is than classical computing.
Mm.
And so there's also an increased richness in Bayesian statistics as opposed to uh, frequentist.
I had
So
no idea. That's amazing. Maybe then, in order to teach Bayesian statistics, we should teach quantum field theory, and then that's an easier segue. What do you think?
for me, perhaps, but
N of one.
I don't know that I would be in the
Not
majority
Mars
for that.
learning path. Yeah.
Yeah.
Interesting. And do you think that allows for any like that's a cool, neat insight, I guess. Do you feel that might allow for any borrowing of or like progress to be made in Bayesian modeling by borrowing concepts from quantum field theory?
Um, I don't think that I'm the only one with these thoughts. A lot of physicists go into data science and modeling, so
Mm.
there are already a lot of smart people thinking about these things, and but I enjoy joining them. And uh, I think there are things have to be adapted. Uh, what to what I find, in other words, like in theoretical math, you don't have to worry about computational complexity. So you have to make a lot of approximations when you go in the machine learning type direction.
All right.
Like you're considering gradient descent because you can only compute the derivatives to first order. Because if you want to use the information about the Hessian, that would be an n squared problem. So
I guess that is the divide between like the theoretical and the very applied statistics all the way to data science, where yeah, the computational aspect, right, which
yeah,
is adds a lot of constraints and creativity and its own sort of tools. And I guess like I would imagine that that is a big part of your transition from like you got the math down, but then how to actually implement that and make that scale and run it and use it to solve applied problems is a different type of challenge.
yeah. So in a way, but I also felt like I was always a very sort of implementation based mathematician, a lot more than
An
my
applied
colleagues.
theoretical mathematician.
Something like that. Like I had to actually uh, I felt like I needed to code things up.
Hmm.
Yeah, I also trusted computer computations a lot more than hand computations. If you're doing something with a lot of sign changes, then that's really hard to get right. So
Yeah,
I use computers a lot since forever.
yeah. Very cool. Well, that was fascinating to hear and learn about. Thanks so much for sharing those insights. Thanks so much for making PyMC installation seamless, and for being part of the community.
Yeah, thanks a lot for having me here.
Pleasure.